I want to do another example with inductors in a circuit. Let's imagine that we have a circuit and we've got a battery here. We can make it 12 volts. And we've got inductor, resistor, another resistor. Okay. Let's say that we have another resistor, an inductor, and then we can connect all these together. And let's say this is 100 ohms, 100 ohms, 100 ohms. Okay. And so what I'm going to do is close the switch. When I close the switch, I have two questions. Okay. The instant I close the switch, how much current flows, and then how much current flows later. So first of all, at t equals 0, the switch is closed, and b, t equals a long time later. Okay. And so when we first close the switch, what happens? When we first close the switch, so close switch, then the inductors don't want to have current flow. So it doesn't really matter what the inductors are. If current doesn't flow, then that means there's no current flowing through this path or that path. The only current flows to the middle path. And so that means the resistance is 100 ohms. Okay, so that means the current is going to be 12 volts over 100 ohms. So that would be equal to 0.12 amps. Okay. All right, so next question. Okay. After a long time, what happens? Well, after a long time, the inductors act like wires. So that means we have three 100 ohm resistors in parallel. So the total resistance is going to be 33.3 ohms. And so that means that the current, which is going to be 100, 12 volts divided by 33.3 is going to be equal to 0.36 amps. Okay, so this is the difference between transient behavior when you first close the switch and then long-term or steady-state behavior after it's settled down a little bit. And this is what these inductors do for you. They resist the initial change and they try to keep the current flowing or doing whatever it was doing. One example of this also is, for example, if you have an electric motor, okay, and you got an electric motor. Remember, an electric motor is a coil of wires, and you got current flowing through it, and then you unplug it from the wall. Then what happens is you're going to get a spark because this inductance tries to keep current flowing for a while afterwards. And so as the current continues to flow, then what happens is that you end up with the current with a huge voltage and then a spark. Okay. Another example is that lightning arresters. One of the simplest form of lightning arresters is, and I think I might have mentioned this before, is that if you've got power lines here and you have a little loop up here and then power lines like that lightning strikes here, the current tries to go around the loop, induces a magnetic field through here. So as the current goes to the loop, you can induce a magnetic field, which exerts a voltage back that way, which keeps the current from flowing further. So it limits the current, the spike from the lightning to that side of the arrestor. And so you sometimes see these things. You see them a lot in rural areas, and you sometimes see them in older parts of town where they did this. In newer parts of town, for some reason, I don't know why they don't do it as much, but that's a cheap lightning arrestor. And again, it's acting like an inductor, not a very good inductor, but good just enough, and that is all that you need. And so it limits transient behavior.